Let's discuss Frieze groups. They are part of the crystallographic groups, which are groups that describe the symmetries of patterns in space. These patterns in space are characterized by the dimension of the Euclidean space in which we work, as well as the dimension of the translation lattice that is part of the symmetries of the pattern. For instance, we have the one-dimensional crystallographic groups, which are in one-dimensional space, and as discussed in the video on one-dimensional crystallography, they are basically trivial, a reflection, and then we are in the one-dimensional case with zero-dimensional translation lattice, or they could contain a translational lattice alone, or a reflection and a translation, and in both the latter cases, we are in the case of a one-dimensional space with a one-dimensional translation lattice. Now there are also two-dimensional crystallographic groups, and they can have, well, a zero-dimensional translation lattice, which I will not discuss, or a one-dimensional translation lattice, or a two-dimensional translation lattice. When they have a one-dimensional translation lattice, that is the subject of the groups of today, which are the Frieze groups, because they are the symmetries of friezes. Let's discuss again how formally these crystallographic groups can be described. So we have a Euclidean space, and we map a point x to a point x prime by a rotation or reflection, in a case an orthogonal transformation, plus a translation. And we recall that it could be that the translation actually depends on the element m, which is part of the point group. Now, a frieze can be described as a horizontal pattern in two-dimensional space. And so, what are the possible symmetry groups of the pattern? So, the first case, well, we won't discuss trivial cases like a completely homogeneous pattern, or no pattern at all, or a zero-dimensional translation group, we don't discuss. So the first case is if we have just translations. So we might have a pattern, a random pattern like this, and then repeat it at various places, repeat it everywhere. This goes in two directions. So this is just translations, one-dimensional translations, because we are in the 2,1 case, always. So the second case is when we have translations combined with a reflection. So let's imagine what their possible reflection symmetries could be. Well, our frieze could have a reflection symmetry which is vertical. So then if we have a pattern like this has a vertical reflection symmetry, and then we can just repeat it. So this is a translation symmetry plus a vertical reflection symmetry. Now, there is another reflection symmetry to our frieze. It could be the reflection in the middle. We could reflect over this axis. So then we could have this pattern, for instance, and then just repeat it, because we always have translations. So we have translations and horizontal reflection symmetry. Now, of course, we can have both, which gives our fourth symmetry group. We can have both horizontal and vertical reflection. So then we might have a pattern like this, plus translations, like that, goes on. And then we have a translation, a horizontal reflection symmetry, and a vertical reflection symmetry, which of course then gives rise to a rotation over 180 degrees, which is also a symmetry of this pattern. Because two reflections which have over axes that have a 90-degree angle give a rotation of a 180-degree angle, which is indeed also a symmetry of our basic two lines in which we put our frieze. So this is the fourth pattern. A fifth pattern is given if we just try to have no reflections, but only that rotation that we just discovered. So we take a pattern which has none of these reflection symmetries, but which does have a rotation symmetry. So that's a point reflection in 2 dimensions, which is not really a reflection at all, but okay. And there we go. Pattern like this, which is should be symmetric if we rotate it by 180 degrees, and then but has no horizontal nor a vertical reflection symmetry. So this can be drawn better, but basically we have a translation and a rotation over 180 degrees. That's the 5th pattern. Now there are new and interesting patterns. The 6th pattern is if we have a glide reflection. So we take a pattern and then we mirror it, but we combine the mirroring with a translation. So here we see the case of a translation depending on the reflection entering our definition of our crystallographic group. So, and then we continue this pattern. So of course there are still translations. So here I need to draw it like that. And then it is inverted again, like that, and so on. So this is called a glide reflection, because we glide and reflect. And our group basically has glide reflections, which then also generate translations. We also can have more symmetry using a glide reflection and a vertical reflection. So we need to start with a pattern which has a vertical reflection symmetry, like this one, over this axis, if drawn accurately. And then we glide reflect, like this. And we glide reflect again. So that we have a glide reflection. Of course, that gives translations, but we also have the vertical symmetry. And then if you look carefully, there is a rotation symmetry also around this axis, because of course this contains a reflection, this contains a reflection, so there should be a rotation symmetry as well. So this is the 7th pattern, and it's actually the last one. So we have 7 frieze symmetry groups. So this is classified, and one can make various attempts to see whether one can find another group, and one will of course fail because this is a mathematical theorem. And one example is if you try to have a vertical glide reflection symmetry which is vertical, well, that will just, because we have a translation and just a reflection like this is like in our one-dimensional discussion of one-dimensional crystallographic groups, and in fact this will just be a vertical reflection over a slightly shifted point, and then we also have translations. So this again falls into the classification we had before. It was one of our 7 already mentioned Frieze symmetry groups, and this is the case for any symmetry pattern that you might construct in 2 dimensions with a one-dimensional translation lattice. You will always find one of these 7 Frieze groups.